Welcome to Prospective Doctors MCAT Podcast, brought to you by Med School Coach. Each week, Sam breaks down the highest yield MCAT topics so you can score as high as possible on test day.
Hello and welcome to Prospective Doctors MCAT Basics with your host, Sam Smith. The goal of this podcast is to cover the highest yield topics on the MCAT and provide you with some sort of insight into the questions that the MCAT really likes to ask. This podcast is going to cover circuits. So I'm going to go over the different circuit variables, things like voltage, current, resistance, and power. Then I'm going to get into circuit elements, things like resistors, sources of voltage, which are also called batteries. I'll talk about capacitors and a little bit about switches. And then lastly, I'll go over Kirchhoff's law and Ohm's law. And this material is going to show up on one out of the four MCAT subsections, and that is going to be the physics and chemistry section, because obviously it's a physics topic. And it is a pretty important physics topic in terms of the MCAT. You know, light and optics are definitely up there. You'll see quite a bit of decay. But, you know, circuits is right up with there with those other topics. So this is very important. It goes along quite well with the electricity and magnetism podcast that I produced earlier. So if you haven't listened to that, I would probably listen to that before I listen to this one. It gives you more of a theoretical background on how a lot of these devices work. So let's get into it. All right, so obviously circuits are kind of in everything. You got your phone, your computer, all these electronics have circuits in them. And we are only really going to talk about these really simple circuits, things that you've seen probably in your Physics 2 class. And a circuit's basis is the fact that you have a flow of electrons that produces a current. And I'm going to get into more of what a current is and talk about this flow of electrons. Just understand that the whole basis of a circuit is flowing electrons or flowing charged particles. And circuits are made up of a bunch of different components. You can have resistors, capacitors, voltage sources, which are usually batteries. You can have switches. And there's a ton of different components. You know, there's ones that I'm not going to talk about here, like transistors, which are used to actually amplify electrical power within a circuit. But before I get into those different components of circuits, let's first talk about circuit variables, things like current, voltage, resistance, power. What are these things? So I want to start by talking about current. So current is the rate at which charge flows through a surface. And in most cases, this is going to be through a cross-section of a wire in a circuit. So you can imagine taking a pair of like wire cutters, cutting a wire, and now you have this cross-section of a wire. You're looking straight at it, and it's going to be a circle, right? This cross-section is going to be a circle. And so now you're looking at how much charge is passing through that area per time. So, you know, this is like, for example, how many footballs can I throw through a hula hoop during a given time? So you're looking basically just at this cross-section, and you're counting all the charges that are going by, 1, 2, 3, 4, 5, etc. And current has units of amperes, which also are known as amps, or abbreviated by the letter A. And this was named after a French scientist, André Marie Ampère, who was a pretty interesting dude, thought that we should be taught through nature. So he believed that instead of going to class somewhere, instead you should just be able to go out into the forest and look at nature and run your own experiments, etc. But, you know, for some people, I'm sure this would be great. But for others, you'd go out in nature and you wouldn't learn shit because you just sit around or, you know, you'd camp. I don't know, but kind of interesting. Anyways, the units of an amp are coulombs per second. And again, coulomb is a unit of charge. So going back to the definition that current is the rate at which charge flows through a surface, then you can say, okay, I see that makes sense, right? Coulombs per second. We're just measuring the charge through a surface for some time. And it's important to note that this charge is actually carried by some charge carrier. So in the terms of many of our circuits in your iPhone or, you know, your power outlet or whatever, this is in terms of electrons. So charge is carried by electrons. I'm sure there's other examples where you have positrons or flow of some other charge carrier that produces a current. But in the case of many of our electronics in the US, and also in terms of the MCAT, think about this as the movement of electrons. And interestingly, this isn't movement in the sense of like water in a pipe. It's not, these electrons aren't moving linearly through this wire. They're not going from the beginning of the wire and traveling all around, and that's what the current is. Instead, what they're doing is they're actually kind of nudging each other. So imagine you have a big row of electrons. They're all kind of sitting next to each other. And then at one end, the first electron gets this nudge. And so when that electron is nudged, it nudges the next one, which nudges the next one, which nudges the next one. And you get this wave that kind of travels through around the wire as each of these electrons nudges each other. So do, nudge, 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 till that current travels all the way through the circuit. And I kind of like to think about this as like doing the wave at a baseball game, right? You know, everybody goes up in the air and goes, woo, puts their arms up in the air. It's that same kind of concept. It travels all the way around the stadium. It's not like one person is running from one end of the stadium all the way to the other that creates the wave. Instead, it's each person kind of goes up and then the person after them goes up, and you just do that all the way around the whole stadium. Well, in the same way, these electrons don't actually travel all the way through a circuit. Instead, they kind of nudge each other so that wave goes all the way through the circuit with them only barely linearly moving. And so that's an important point to make too, is these electrons do move linearly, but this is not what produces the electricity that we think of. So there's something called electron drift velocity, which is how fast electrons are moving linearly. And this is really slow, actually. This is something like a millimeter per second or 0.002 knots if you're a boat. That's how fast you'd move. And therefore, it takes these electrons about 30 seconds to drift an inch. So they move really, really slow, right? Imagine turning on your lights and having to wait like 2 hours for these electrons to move all the way up and, turn on your light. It'd be annoying. It would take forever. And another interesting thing to mention here is that the direction of current is actually opposite to the direction of electron flow. And all this is a sign convention thing, because current is defined as the flow of positive charge. And because electrons are negative, then current is technically in the opposite direction as the negative electron flow. So a little bit confusing, yes, but just remember that current actually flows in the opposite direction as the electrons. And so right now you might be having a little bit of cognitive dissonance because I defined current as the movement of charge per time. But then I went on to say that these electrons are not actually flowing in a circuit. Instead, they're kind of just pushing each other, bumping into one another, and that's what's being carried around the circuit. So how do you hold these two views at the same time? Well, I like to imagine it like this. So let's go back to our point of view where we have all these electrons lined up in a wire and they kind of nudge each other, and that's what carries that current. Well, now let's think about them as playing hot potato. So the first electron's got a potato, passes it to the next, passes it to the next, and so you have this potato that's kind of being hopped along these electrons down a wire. You can think of that as the flow of a charge. And so again, these electrons are charge carriers. They're not necessarily charged themselves. So instead of thinking about these electrons moving through a circuit and that's the movement of charge, instead it's like the charge is passed along from electron to electron like a hot potato. And that is why we can say that current is the movement of charge per time, because we're looking at charge itself, not charge carriers. So in this example of the potato, current would be how many potatoes are passed along by the electrons per time. So you take a single cross section of your wire and you look and you see, okay, how many potatoes are passing through per second, per minute, per hour, whatever unit of time you want to do. All right, so just to quickly recap for you, the things I think that you really want to know about current are, number one, its definition, the rate at which charge flows through a surface per unit time. And then you want to know that this is measured in coulombs per second, which is an amp. And then you also wanted to understand that the flow of electrons in a wire is in the opposite direction as the direction of current. Or in other words, current flows in the opposite direction as electron movement. And that is based on sign convention that says that current is the rate of movement of positive charge. All right, let's move on now to the next circuit variable, which is voltage. And so voltage is a measure of electric potential difference. And it's very important for circuits. This is essentially what drives these charges to move around a circuit. And so real briefly here, I want to kind of remind you what exactly electric potential is, just because it plays such an important role for voltage. And this is all back in the electromagnetism podcast, but I'm just going to quickly recap this. All right, so I'm going to give you the boring-ass physics definition of electric potential, and then I'll break that down in kind of more basic terms. So electric potential is the amount of work needed to move a unit of positive charge from a reference point to a specific point inside some electric field without accelerating that positive charge. In other words, you have some charge, you take this charge and you tape it to your finger. Now, you put your finger in an electric field. And what does an electric field want to do to a charge? Well, it wants to accelerate that charge. And so all electric potential is the work done by your finger in moving that charge that's on your finger from one point in an electric field to another point in an electric field at a very slow pace that does not change that particle's acceleration. In other words, you're not accelerating from one point to another. Instead, you're just moving with a constant velocity from one point to another within that electric field. And the electric potential is the work done by your finger in this case in moving that particle, right? Because the electric field wants to move that particle, but you're going to have to put some work in order for that electric field not to change the trajectory of that positive particle that you have attached to your finger. Another way to think of this is in terms of mechanical potential energy. So electric potential is very analogous to mechanical potential energy. So you can think of the potential energy associated with a ball rolling down a hill. Well, when the ball is at the top of the hill, that is high potential energy. And then you dissipate potential energy as that ball rolls down the hill, right? It's converted from potential energy into kinetic energy, and you reach a state of low potential energy at the bottom of the hill. In the same way, positive charges move from areas of high electric potential to low electric potential, and they accelerate when they do so. So you can see there is quite a good comparison to mechanical potential energy. And so in the end, all electric potential does is it causes charge to flow. It causes charge to move, right? Positive charge from high potential to low potential, negative charge from low potential to high potential. In the end, that's all you really need to understand. Electric potential causes charges to move. So that's kind of a brief recap of electric potential. Let's now apply this to voltage. And so again, voltage is a measure of electric potential difference. So for example, let's take a battery. So if the battery has a positive terminal and has a negative terminal. And so at these terminals, there is a big difference in electric potential. So at one end of the terminal, the positive end, you have a lot higher electric potential. At the negative end of the battery, you have much lower electric potential. So what that does is it causes these charge carriers to move from the positive terminal, high potential, to areas of lower potential, the negative terminal of the battery. So for an analogy, voltage is somewhat like pressure. So, right, a battery is like a pump. What a pump does is it increases the pressure, which then causes fluid to flow from high pressure to low pressure. Well, in the same way, a battery increases the potential and causes charge to move from high potential then to low potential. And in terms of units, voltage is defined as electric potential energy per unit charge, which is known as a volt, and that is joules divided by coulombs. And this is named after this dude who has a sweet name, and that is Alessandro Giuseppe Antonio Anticio Volta, which, shit, he has three middle names. I wish I had three middle names. That's pretty cool. And you also might hear voltage called electromotive force, or EMF, because it causes these charge carriers to move around. It kind of exerts a force on these charge carriers that moves them around. So that is a little brief introduction to voltage. I think the main takeaway here is to understand that voltage just has to do with the difference in electric potential. And so this is kind of like the driver that causes these charge carriers to move around and produce a current. So it is the pump to, a pipe system. It's what causes motion. It's what causes current. Let's now move on to the next variable in a circuit, which is resistance. So resistance is kind of the opposite of conductance, which is essentially how good a material is at conducting electricity. So, rubber, It's a bad conductor. That's why you put it on the outside of a wire, also known as an insulator. But metals, on the other hand, they have these free electrons that are kind of floating around and can be bumped along, passing charge, and therefore they are good conductors. So resistance then is a measure of the opposition to current flow in an electrical circuit. So let's now go back to my analogy of the football and the hula hoop. Again, the hula hoop is supposed to represent a cross-section of some wire, and a football represents charge that goes through that cross-section of the wire. So imagine I'm throwing these footballs and this charge. It's going through the hula hoop until 4-time NBA champion and 15-time NBA All-Star Shaquille O'Neal comes up and starts swatting these footballs so that they can't make it through that hula hoop anymore. Well, now you have something that's impeding current flow, essentially is a resistor. And resistance is measured in a unit called ohms, which is abbreviated with the Greek letter omega and is volts per amp, or V over A. And it was actually named after this guy called George Simon Ohm, who was a German physicist who published Ohm's law in a publication, or I think a book, called The Galvanic Circuit Investigated Mathematically. So he is the very smart guy who is to thank for Ohm's law and all these fun circuits problems that you're going to see on the MCAT. And so there is a very handy equation that goes along with resistance, and it is that resistance is equal to rho times L over A, which is resistivity times length divided by area is equal to resistance. And so resistivity is a property of whatever material you're using. So if that's a metal, it's probably got a pretty low resistivity. If that's something like rubber, it's probably got a pretty high resistivity. And then length is however long this unit or resistor is. Then A is the cross-sectional area of this resistor, or maybe you're looking at a wire. Whatever unit you're looking at, A is the cross-sectional area of that. And this equation is probably one of the more important things to understand about resistance, and something you'll definitely see on the MCAT. And so really understand the relationship between these different variables in resistance. So for instance, as the length of your wire or the length of your resistor increases, the resistance also increases. And then on the other hand, if the area of your wire or your resistor or whatever you're looking at decreases, then that's actually going to increase the resistance. So just have a handle on this equation, understand what happens if I change length, what happens if I change area, what happens if I change resistivity, what does that do to the resistance? The last thing that I want to mention here is the relationship between resistance and temperature. So as temperature increases, resistance also increases. So this is a little bit kind of counterintuitive, because you'd think that if your temperature is going up, maybe you'd get more current flowing through this resistor, there'd be less resistance. But in fact, it's the opposite. Resistance actually increases with increasing temperature. So that's just something to kind of maybe put on a flashcard, keep in the back of your mind. That might come up at some point on the MCAT. All right, so that's a resistance. I think the most important thing to understand here is that this is a property of the material itself. Unlike voltage, unlike current, this has a lot more to do with the type of material that you're using. So that's something to keep in mind. With that, let's move on now and talk about power. In physics in general, power is defined as work per time. And the same thing goes for electrical circuits. Power is measured in joules, which is work, per second, which is time. So in electrical circuits, power is joules per second. And in an electric circuit, power is defined to be the rate at which energy is transferred from electrical energy to another form of energy. So, for instance, you go from moving charges to heat, or from moving charges to light. So this is just the rate at which you transfer this energy of moving charges to, let's say, light in a light bulb. So, this is to say I am transferring 4 joules of energy per second from my circuit to a light bulb, and that is being shown as visible light. And I think this is really kind of the main way that you'll see this presented on the MCAT. You'll have a circuit with light bulbs, and it'll say, you make some change to your circuit, and what is going to happen to these light bulbs? Are they going to shine brighter? Will they shine the same? Will they turn off, etc.? And so the big thing to understand here is that a light bulb will shine brighter if it sees more power. And why is that? Well, essentially what's going on is that you are converting more electrical energy to thermal energy in the light bulb filament, which in turn makes the filament glow brighter than before because it's hotter. So this obviously only works up to a point, right? Because if you start transferring too much energy, then shit's just going to blow up. But the big key takeaway here is that power is the transfer of electrical energy from one form to another. And on the MCAT, you'll probably see this presented as brightness of a light bulb. The higher the power in a circuit, the brighter a light bulb will be that's connected to that circuit. And there's some equations you can use to actually calculate power in a circuit. And these go along with Ohm's law, which I'm going to talk about in a little bit. But just know that power is equal to current times voltage, which is also equal to current squared times resistance. So you can use those to calculate power and solve problems within, circuits on the MCAT of, maybe they ask you a question where they say, I increase the voltage in a circuit. What's going to happen to this light bulb? Is it going to be brighter? Is it going to be the same brightness? Is it going to get dimmer? Well, obviously, if you increase the voltage, you increase the power, and so that's going to be a brighter light bulb.
Thanks for checking out the Prospective Doctor MCAT Basics podcast. Sam's doing a killer job taking you through the most important MCAT topics, but what if you need a little extra help? How does a 5, 10, or even 15-point increase in your score sound? Imagine how your chances at admission could increase. Med School Coach's MCAT tutoring can get you there. With the most rigorous selection process of any tutoring company, we see amazing results. We deconstruct each student, find a plan that is going to work, and help execute it. That's why our students add an average 12 points to their score. Completely physician-run and operated, and focusing on nothing but medicine. It's no wonder over 10,000 past students have trusted Med School Coach to get them through the MCAT and into medical school. Check out medschoolcoach.com today and mention code PODCAST for 5% off.
All right, so there are a few different circuit elements I want to talk about. The first is a resistor. The second is a battery or a voltage source. The third is a capacitor. And then lastly, I'll briefly mention switches. And before I get into talking about these different circuit elements, I want to briefly bring up Ohm's law. So Ohm's law says that the voltage in a circuit is equal to the current times the resistance. So V equal to IR. That's kind of the main relationship to know. And then obviously too, you can use that to calculate power. Power is equal to voltage times current, or P equals IV. So really what's going to happen on the MCAT is you're going to be given, one or two of these variables, and then maybe they say one of these variables is held constant, the other variable goes up. What's going to happen to the third variable? So really, you just need to understand the relationship between these variables, as with all, questions on the MCAT, really, for physics at least. Understand the relations between these variables and how to apply them. All right, so let's get into the first circuit element, and that is a resistor. So resistors apply resistance to a circuit. And that might make some sense. We just talked about resistance. That is the opposition to current flow. So these little elements resist current flow. But, why are they involved in circuits? Why can't we just have a circuit where there's no resistors, so the current's just free to flow wherever it wants to go, as fast as it wants to go? Well, too much current can actually be a bad thing. So take this example. Let's say that you don't have a resistor attached to a circuit. So you just have this battery and it's connected to just a wire. Okay, well, how much resistance is in a wire? Well, it's a really, 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 really low amount of resistance. So almost zero. Now, let's look at the current. So you have this battery that's a set voltage, and you have a resistance that's very, 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 very low in a wire. Now you take your Ohm's law, V is equal to IR, you divide over the R, So now you have the current is equal to the voltage over the resistance. So we have this set voltage and this really, really, really low resistance. Well, now you have a current that is really, really, really high. You almost have an infinite amount of current. And why is that bad? Well, as you could imagine, this starts to get really hot, starts to heat up, and you can actually blow up the battery that you're using. So all this is to say that resistors are important because they slow down current and they dissipate energy in a circuit. And so that's kind of one of the main things to understand about resistors. They're important because they dissipate energy in a circuit. The next thing to know that's important is what happens when you connect resistors in series versus what happens when you connect resistors in parallel. So before I get into what exactly this means for resistors, let me just talk about in general what it means for components in a circuit to be connected in series versus parallel. So in series, components are connected to one another in terms of train cars and a whole train. So you have the first component and that's connected to the second, which is connected to the third, which is connected to the fourth. If you don't know what I'm talking about, just go Google this real quick and you'll easily see this. And then in parallel, I like to think about this as branches on a tree. So you start with a main branch, that's your main wire, and then from there you split off into, 1, 2, 3, 4 different branches. And from there you run those branches through components and then you come back into a single branch. And so, these components would be considered in parallel. And again, if you have no idea what I'm talking about, please just go Google this, look at an image. I'm kind of assuming that you took Physics 2 and you have some idea of what resistors in parallel versus series look like. The important thing to understand here is what this does to the overall or total resistance in a circuit when you have multiple resistors either in parallel or in series. So when you have resistors that are in series, all you have to do is add up those resistances in order to calculate a total resistance. So let's say I have a circuit and I have a 6-volt battery and it goes and it's connected to one resistor, which then goes around connected to another resistor, goes around and connects to the negative terminal of the battery. One of these resistors has a resistance of 2 ohms. The other resistor has a resistance of 4 ohms. The MCAT is then going to ask you, something about the voltage drop across each of these resistors, or maybe it asks you about the current in the circuit, or maybe it just asks you to calculate the total resistance. Well, all you would do is add 4 plus 2, which is 6, and now you can either use that to calculate the current in the circuit using Ohm's law, or you just plug in, for the answer and say, okay, the total resistance in the circuit is 6 ohms. Now, when you get to resistors in parallel, it gets a little bit more freaky, a little bit more weird. You get this equation that is 1 over the total resistance is equal to 1 over the resistance of the first resistor plus 1 over the resistance of the second resistor plus 1 over the resistance of the third resistor and so on. In other words, the reciprocal of the total resistance is equal to the sum of the reciprocals of all these resistors that are in parallel. So let's go back to the circuit that I was talking about before, which is the circuit that we have that has 2 resistors, one that is 2 ohms and one that is 4 ohms. Let's take this circuit and now say that these resistors are connected in parallel instead of in series. Now to calculate the total resistance, I just use the equation I was discussing previously and say that 1 over the total resistance is equal to 1 over 2 plus 1 over 4. So 1/2 plus 1/4, that's 3/4. Now I take the reciprocal of that, and now we get a total resistance of 4/3. So the big takeaway here is that when you have resistors that are in series, all you got to do is add them. That's like the easiest thing the MCAT could ask you. But if you're given a problem where you have resistors in parallel, now you have to use this weird, wacky equation where you have a bunch of reciprocals added up, and then you can solve for, whatever you're trying to solve for in these problems. And so this brings me to another important point, and that is that resistors connected in parallel will have a smaller total resistance than resistors connected in series. And so why is that important? Well, let's just say that you have 2 circuits, and the only difference between these circuits is that in one circuit, you have resistors in parallel versus series. You have an 8-volt battery connected to each of these circuits. So now you use Ohm's law, which is V is equal to IR, to say that the resistance is lower in this parallel configuration of the circuit, and therefore your current is going to be higher. And so using this reasoning then, you can say that in comparing a circuit in which the resistors are connected in series versus parallel, the current is higher in the circuit that's connected in a parallel manner. And yeah, that's kind of specific, but what I really want you to understand here is that what the MCAT's going to do is it's going to present you some situation you've probably never seen before, something you don't have memorized, and you're going to have to take these equations, Ohm's law, for example, and then apply it to the situation and say, okay, well, I know the resistance is lower here, so that means the current must be higher, and then solve that problem. So the MCAT is not about memorization. It's all about learning equations and knowing how to apply these equations. And just a quick anecdote before I move on to the next topic. If you look at these old traditional Christmas lights, a lot of them are actually wired in series. And so what that means is that if one of the bulbs in this whole series goes out, then electricity can't keep flowing and none of the rest of the light bulbs work. And so, this leads to good memories of my dad plugging in a set of Christmas lights to the wall and then being like, oh, God damn it, who broke one? And we'd have to search around and find, okay, this light bulb's burned out, then we'd have to try to replace that. And if that wouldn't work, then we'd have to go replace another. So I think nowadays a lot of them are connected in series, and therefore when one of these light bulbs goes out, the circuit is not broken, current can flow, and all of the other light bulbs are still lit up. And it's a lot easier to find out, which light bulb isn't working. Okay, replace that because they're lit up. Anyways, just a little story, something maybe help you remember what series versus parallel circuits look like. All right, the next thing I want to talk about here in terms of circuit elements is a voltage source or a battery or an EMF. You'll see it a few different ways on the MCAT. And so what's important to understand here is this is like the pump, as I said earlier, in some kind of water system. This supplies the energy that drives, it charges around, and creates a current. And there's one thing here that I really wanted to hit on, and that is that you can have ideal batteries and you can have non-ideal batteries. The difference here is that ideal batteries have no internal resistance, whereas non-ideal batteries have some internal resistance. And as I'm sure you could imagine, non-ideal batteries are what batteries are like in real life. You have some kind of internal resistance, some kind of resistance to the movement of current within real batteries. They're not perfect all the time. And so if you see some kind of non-ideal battery on the MCAT, and you're not likely to see this, just treat the resistance they give you like a normal resistor in series with an ideal battery. It's pretty easy, right? You're going to have some voltage drop across this resistor. You can use Ohm's law to then calculate how much voltage is actually supplied by this battery. So the takeaway here is that batteries are the driving force that push charged particles around circuits that create current. And then you can have non-ideal batteries, and all you got to do is take into account the internal resistance of the battery, treat it like a normal resistor, and you can solve any problem doing that. The next circuit element I want to talk about is a capacitor. And so capacitors are able to store little bits of energy in a circuit after they have been charged up. And so they have a lot of important applications within electronics. For instance, if your computer is losing power, it may not actually be able to shut down safely to save all your files, but some computers, and I'm guessing older ones, have capacitor arrays that are actually able to store energy that can be used then for safe shutdowns and be able to provide a little bit of energy in order for you to save critical files and limit the damage from your computer crashing and burning or whatever it's going to do. And so there's a single kind of capacitor that you are most likely to see on the MCAT, and that is the parallel plate capacitor. And it looks like exactly what it sounds like it looks like. It's essentially two plates that are parallel to one another that are connected to a circuit. And so, you can imagine this is like two sheets of paper that are really close to each other, not quite touching, but really, really close. And typically these plates are separated by a type of material that's called a dielectric material. And this is a polar material that is a very bad conductor. That's to say that it does not really conduct electricity or pass charges through it, but instead what it does is it supports an electric field or likes an electric field or, maybe loves, I don't know. I'm not sure if it goes that far, but it really likes an electric field. And that is because it has polar molecules that are able to line up with the electric field. And that's important because in between the plates of a parallel plate capacitor, there's actually a uniform electric field. So just keep that in mind as I talk about this. There is a uniform electric field in between the plates of a parallel plate capacitor. Further, this uniform electric field is actually equal to V over D, or the voltage supplied by the battery over the distance between the plates. So be able to use that equation a little bit, in terms of the electric field between these plates. If you increase the voltage of a battery, then this tends to increase the electric field between plates if you have, of course, a capacitor connected to the battery. And then if you increase the distance between these two plates in the parallel plate capacitor, that tends to decrease the strength of the electric field. All right, so far we know that capacitors store energy, and the most common one that you'll see on the MCAT is the parallel plate capacitor, which has a uniform electric field between its plates. Let's move on now and let's talk about what exactly capacitance is. And so capacitors have capacitance, which sounds like it doesn't mean anything. That's like saying, oh, hey, I like your face. It's very facedness. Like at that point, you'd be like, oh, thanks. But anyways, so capacitance describes how good a capacitor is at holding charge or storing charge. And capacitance is abbreviated with the letter C, and it's measured in farads, which is coulombs per volt. In other words, this is saying that for every 1 volt that's supplied to a capacitor, it can hold X amount of charge. So that should help you really see what capacitance means, right? Coulombs per volt. For every volt that I feed you, if you're a capacitor, you can hold, this amount of charge. So the higher the capacitance, the higher the amount of charge you can store per volt of energy supplied to you. And so as I'm kind of alluding to, there's an equation that is typically associated with capacitance, and that is Q over V, which again is charge over voltage. So just remember that capacitance is equal to Q over V. And this equation applies to every single capacitor ever. It doesn't matter if it's parallel plate, if it's, whatever other kinds. I forget what the other kinds of capacitors are called. Doesn't matter. For the parallel plate capacitor specifically, there is an equation that is associated with it. That is, capacitance is equal to E times A over D. And it's the Greek E. And I don't even know. I think there's a real word for that, and it's lowercase epsilon. So it is A times lowercase epsilon over D. And in this case, I'm just going to say E. E is the emissivity constant, which is 8.8 times 10 to the minus 12 farads per meter. And A is the area of the plates, just, length times width. And then lastly, D is the distance between the plates. And as always with the MCAT, you really just need to know the relationship between these variables. Yes, they might give you numbers and you'll have to actually solve for the capacitance or something, but more likely it's going to ask you, what is going to happen to the capacitance if I increase the area of these parallel plates? Well, the capacitance is going to increase if you know this relationship. You can also think about it in terms of how much charge can these plates hold. Well, if you increase the area, these plates can now hold more charge. So I like to think about it that way too. And then what happens if you decrease the distance between the plates? Well, that's also going to increase the capacitance. What happens if, I flick the plate or I bop it, twist it, pull it?
Flick it, pull it, pass it.
Definitely my favorite game growing up as a kid, by the way. So anyways, moving on to the next thing to know about capacitors is what happens when I hook capacitors up in parallel versus series. Well, for me, this is kind of the easiest thing to remember because I think back to what I know about resistors. So when I put resistors in series, I know that it's just additive. And then when I put resistors in parallel, I know that we have this weird reciprocal addition. Well, just know that for capacitors, it's literally the exact opposite. So capacitors in series, you have to add them using this weird reciprocal addition, and then take the reciprocal at the end, find the total capacitance. And then when you have capacitors in parallel, you just add up the capacitance of each of these capacitors to get the total overall capacitance. Now I want to quickly go back to what I was talking about at the very beginning. I was talking about how capacitors can store bits of energy, and then they can actually discharge this energy at some point, when needed in a circuit. And so I hope you're starting to think back to RC circuits, which are resistor capacitor circuits. These were the circuits that you had to do actual legit calculus on in order to be able to tell what the current was, because current's changing over time, and I don't remember the exact derivative you have to use, but you have to use a pretty specific equation. It's really not important for the MCAT, but essentially what's going on is you're charging up your capacitor. So you have your capacitor and it's plugged into some battery, and over time, fairly quickly, what's going to happen is you're going to start charging the plates of the capacitor. And so on one of the plates, you'll have a bunch of positive charge built up, and then in the other plate, you'll have an equal amount of charge, but it will be negative charge built up. So you keep building up this charge until you reach the maximum charge that can be stored by that capacitor. And at this point, the capacitor is fully charged. And what happens now, and this is usually done by flipping a switch, is you put this capacitor that's fully charged in a circuit with just a resistor. And this is now an RC circuit. And what happens now is that this capacitor, or the energy stored in this capacitor, now drives a current around the circuit, and the energy is dissipated through the resistor. So what happens is you'll get a current flowing for a bit, and then the resistor will continue to kind of give off energy until that current dies down and the parallel plate capacitor has discharged all of its energy. So essentially, a parallel plate capacitor, once it's charged, can act like this kind of short-term battery. It stores a little bit of charge, just enough to get you, over a hump, I guess. If you are some kind of electronic equipment and you're about to shut down or whatever, this gives you a little burst of energy to be able to store files, as I said at the beginning of this segment. So takeaways for capacitors are that, number one, they're able to store a little bit of energy. That's one of the roles they play in a circuit, kind of the most important one to know. And then also know that the parallel plate capacitor is the most common one that's seen on the MCAT, and to calculate the capacitance of a parallel plate capacitor, there's an equation that says that capacitance is equal to E times A over D. And then understand that capacitors in parallel versus capacitors in series are just the exact opposite in their additive properties as resistors. Then lastly, think about how parallel plate capacitors can be charged up and then can be dissipated through resistors, also known as an RC circuit. All right, so the last piece of circuit equipment or circuit element or whatever you want to call it is called a switch. And this is probably the most basic one I've talked about yet, but you're still probably going to see it. And there's a few things a switch can do. So it can totally cut off current if it's open, or if it's closed, it doesn't really do much. It acts like just a wire. But importantly, it can switch the configuration of a circuit. So, when it's in one position, you'll have one circuit, and when it's in another position, you'll have another circuit. If you don't know what I'm talking about, go Google an image of this. Google something like RC circuit with a battery or something like that. But there's one specific RC circuit I'm thinking about, where essentially in one configuration you have a battery that's charging up a capacitor, then the switch flips, and now you have a capacitor resistor circuit and you're discharging this capacitor. So switches, pretty easy to understand. You'll probably see some kind of question that the MCAT might ask where it says, what happens when this switch is open, or what happens when this switch is closed? But really that just goes back to your understanding of circuits in general. All right, the last thing that I want to talk about here is two different laws that apply to circuits. The first is Ohm's law, and I've talked quite a bit about this so far, but I'm going to go over it again. And then the second one is called Kirchhoff's law. So Ohm's law was developed by this German physicist, as I was saying, and this is that voltage is equal to current times the resistance, or V is equal to IR. And this is really change in voltage. So when you're given, an 8-volt battery, that's the difference between the two terminals of the battery. So, you can think about it as delta V is equal to IR, or V is equal to IR. But usually, you'll be given a circuit, and then maybe you'll be given one or two of the variables, asked to solve for the other. Or, of course, you might be asked, proportionality, or so when I increase voltage and keep current the same, what happens to resistance, and so forth, things like that. So just know how to work with this equation. That's all I really have to say about Ohm's law. Kirchhoff's law, or if you were my physics lab partner my freshman year, I like to call it Kirchhoff's law. This says that at a junction in an electrical circuit, the sum of the currents flowing into the junction node is equal to the sum of the currents flowing out of that junction node. And this is honestly pretty intuitive. You can think about it like this. So say I have a single wire, and then that wire splits into two. Well, if you have a current flowing up that single wire and the current splits, well, then you're going to have half the current of that big wire in each of the ones that it splits into. In other words, if you add up the currents from each of those small wires that split off from this bigger one, then those currents added up would be equal to the current in the bigger wire. So it's essentially like a conservation of mass or a conservation of energy, just saying that current can neither be created nor destroyed. And so the actual application of Kirchhoff's law is something that you're not really going to see too much on the MCAT. The actual application is in solving these kind of complex circuits. And so where you'd use it is you would use it to help you solve a system of equations. So some of the equations will come from Ohm's law, and then some of the equations will come from Kirchhoff's law. And so you'll have all these equations set up, for Kirchhoff's law, it'll be something like current 1 is equal to current 2 plus current 3. So that's a conservation of current at some node. And then for Ohm's law, obviously you'll have like voltage 1 is equal to current 1 times resistance 1. And so you get this whole big system of equations set up, and then you solve for all your unknowns. You're not going to see that on the MCAT just because it's too lengthy of a problem. But having an understanding of what Kirchhoff's law says and what it implies, I think is kind of important. You might see some standalone maybe on the MCAT about it. But yeah, so that is Kazakhstan's law. And that'll do it for this episode of Prospective Doctor's MCAT Basics. Thanks for listening as always. I'm going to take a brief few weeks off from doing these podcasts just to write some secondaries for medical school. Good luck to everyone who's out there who's applying for medical school or is still studying for the MCAT. Study hard. Keep in mind that, you're a year away from applying to medical school and it's about to all get super real for you. So study hard, do well. Thanks as always for listening. If you like this podcast, if you think it helped, please go give us a review on iTunes. It helps us in the rankings and helps us reach more students. Keep working hard.
Thanks for listening to Prospective Doctor's MCAT podcast. If you're a pre-med, you'll want to check out prospectivedoctor.com for tons of free tools, articles, and more podcasts that cover your pre-med life. And if you need help on the MCAT or getting into med school, check out medschoolcoach.com for the experts.